Okay, so in this video, what I hope to get together is the receiver side of the transceiver. There's a lot to do, but let's just quickly summarize where we're up to. So what I've confirmed up to this point is the ESP32A1S and the audio switch seem to be working well together. We've got the local oscillator, and we tested that a little while back, and obviously the power circuitry is all good. So what we're going to move on to in this video is the receiver side, and as I mentioned before, that's these green paths here. This is an RF path, this is an audio path, and obviously the output side here. So just to summarize what we have to pull together, the first is the Tayloe detector, which you've seen many times if you've watched any of my videos. Then we have to look at this RF switch, which switches between the receive side and the transmit side. Now for the receiver side, I do need to pull together this band pass filter right here, but I don't need this this PA circuitry right here. And then finally we do need to install the output jack. So we've got a band pass filter to build, we've got the RF switch to have a look at, the Tayloe detector, and obviously all the connections to and from the DSP processing side.
So let's have a quick look where all those components fit on the board. And so the Tayloe detector is right here. Here's the output op amp right here. Here's where the FST3253 goes. This is the RF splitter, and we've got the the Tayloe detector caps and resistors right here. The other part that we need to pull together is the low pass filter, and that'll sit right across here. So there's a couple of headers that'll get installed, and I think you've seen my low pass filter boards from before. I'll be using one of those. And then finally there's this pair of relays, and if we have a look on the other side of the board here, there's some circuitry that goes with those relays to turn them on or off depending on whether we're in receive or transmit mode. A couple of diodes to protect the relays. So one of the other things I've changed since the last video, I've installed this pair of encoders right here, and one of them will be to change the frequency, and the other one will be to sort of do sort of other attendant sort of menu related functions. So what I'm going to first do is just confirm that these two encoders are working correctly. And that there's no problem in terms of the GPIO pins that I'm using there. So I'll move on to that right now. Confirm these two encoders work correctly, and then we'll be able to move on. Okay, so doing some testing with the encoders, I found another little problem on the board, and that is at least with this right encoder here, I'd hooked this pin up to GPIO 34, which is right at the top here. It's this pin here, and it corresponds to the 5th pin down. Now, unfortunately, and I didn't know this beforehand, GPIO 34, and in fact pins 34 through 39 on the ESP32 have no internal pull-up resistors. So this encoder wasn't working at all. So what I have done is basically cut the line to pin GPIO 34 and connected it to GPIO 2, which I have available. So let's go over, and now that I've done that, have a look at the code and test it out. Okay, so there's the board all hooked up, ready to go. Let's just pan up and have a quick look at the code, make sure it's... so I'm using this encoder library that I'll provide a link to. It's one of the Adafruit ones, I think. But so here's the two encoders set up. So basically you can just tell it which pins it's using, and the order of the pins just dictates whether clockwise is positive or clockwise is negative. So anyway, there's the two encoders I have. First one on pins 13, 14. Second one pins 15 and 2. The rest of the code's pretty straightforward, and this is called test encoders. I will include a link to this this little test program. So anyway, let's try. I'm going to turn the left encoder first, and you should be able to see that frequency counter increasing. Now, I think I have a little bit of a problem. These are just cheap encoders. There's a little bit of a problem. You can see it skips there every now and then where it repeats the same values. But that confirms that the frequency encoders looks like it's working fine. And then if I turn the menu encoder, the right-hand encoder, you can see that's working fine. And interestingly, this one doesn't have that skipping problem. So there we go, up and down. So anyway, that confirms at least now that both the encoders are working. I will make a change to the circuit that's up on the GitHub repo to move that from pin 34 to pin 2, and then I'll publish it on the repo. So anyway, what we'll move on to next is the RF switch.
Okay, so let's have a quick recap on the RF switch, and as you can see is a pair of relays. The unenergized position of the relays is in receive mode. So we've got a couple of flyback diodes on there, and basically we have 12 volts on one side, and then that goes off to relay on for both relays. And as you can see up here, so here's relay on, when the radio is in transmit mode, this is high, which turns the fed on, which grounds relay on and allows the relay to be energized. So relay will be energized in transmit mode and it will be unenergized in receive mode. So let's get that together on the circuit and do some testing.
Okay, so as you can see, those two relays are installed, and if you have a look at the back side there, here's the two flyback diodes right here and here. And then here's that FET and resistor combination that basically goes to ground when transmit is enabled. So anyway, let's make sure that the connections are correct by sort of buzzing this out. Okay, so here we are zoomed in, and you can hear those relays clicking as I toggle between transmit and receive. So I've got it currently in receive mode. And in receive mode, there should be no continuity between the LPF, which is right here, and the antenna, because LPF goes to antenna and transmit. You can see that that's correct. So let's just go into transmit mode, and then I'll probe on the antenna and the LPF. And you can hear there's connectivity. So that confirms that the switching here is the correct way around. So there should be continuity between the center pin and over here in receive mode. So let's just go back to receive mode. And it's a bit hard to do this around the camera, but center pin to here should be continuity. And you can hear there's that continuity. So that confirms this top relay is fine. So I've swapped the board over so we can see things a little better. So I'm actually in, let me just change this. Let me change back to receive mode. And in receive mode, there should be a continuity between the antenna and the input of the bandpass filter. Make sure it's still in focus. So there we have. So this is the input of the bandpass filter, and so that's the first component in the receive pass. So that confirms that that's working. And in transmit mode, there should be no continuity between the antenna and the input of the bandpass filter. And you can see that that's the case. So that basically confirms that the relay setup is all correct. So what I can move on to now is, what I'll do is I'll build up the bandpass filter right here, which will be that double tune bandpass filter that I've showed before. It'll be configured for 20 meters because that's what I want this radio on. But obviously the good thing here is I can, because I've got these little pluggable modules, I can, do some testing on some different bands, which I should have done it ages ago, but I never did. So anyway, I'll build up a bandpass filter board, and then we'll do some more testing. Okay, so I've got my little bandpass filter module right here. It's the double tune bandpass filter that you've seen before. The LPF has nothing to do with the receiver, so that was my mistake. So let me just plug that into the radio here, right in there, and then let me plug the turn the radio on so we can change the settings there. Okay, so I've currently got it in transmit mode, and as you can see, I've got the tracking generator on the spectrum analyzer. I'm injecting just after the splitter on the receiver. You can see there's nothing coming through there. So let me turn it into receive mode, and there you can see is a nice trace there for a typical bandpass filter trace. And you can see, if I just have a look at that, the 3 dB point is around about 13.477 megahertz on the low side, and about 15 megahertz on the upside. That confirms that the bandpass filter is functioning correctly. What I'll now move, I have to sort of bite the bullet now, and what I now will move to is putting the rest of the Tayloe detector in place. So that'll consist of the FST3253, this op amp here, the splitter transformer right here, and then we'll be getting close to be able to inject some RF signals in there and see the results. Okay, so I've got all the components for the Tayloe detector installed. There's the FST3253 and so on and so forth. The next thing I'll have to get installed is this FT5043 toroid, and it's going to have 11 turns bifiller, and over the top of that 22 turns single. So the bifiller turns form part of the split side, and then the single turn is fed from the incoming RF. So anyway, let me get that installed, and we'll come back and we'll be able to do some testing at that point. Okay, so as you can see, I've got the splitter installed. I ended up just doing a tri-filler instead of what I'd originally planned, so I actually pilfered this off a separate receiver. And I'm basically tapping on the output right here, which is the output after it has passed through the DSP. So the program I'm using is, for those following along, is called Test Receive in the GitHub repo that I'll include a link to below. So just to walk through the test, as I said, I'm probing on the output of the ESP32. I'm injecting into here a signal at 14.2005 megahertz, and this local oscillator is running at 14.2 megahertz. So the upshot is, let me just pan up so you can see that. So there's the SIGGEN, minus 40 dBms at the frequency I just mentioned. And then if I pan down to the oscilloscope where I'm probing the output, now I'm not doing any DSP at the moment. I'm basically just sampling the output of the Tayloe detector after it has been run a simple I2S in, I2S out. And you'll see that in the test receive program. So as you can see, we're getting a good, it's a little bit wonky there. We're getting a good signal in quadrature, and the output frequency is around about 500 hertz, a little bit less than that, as you can see. So that is the expected sort of output of the mixing product. But to confirm that we're getting it in quadrature, we'll do the old test where I take the frequency down. As you can see, that mix frequency is increasing. So now you can see I'm below the 14.2 megahertz, actually 14.1997. And as you can see now, the yellow trace is leading the purple trace, where it was the purple trace leading the yellow trace. So let me go back up again above frequency. So you can see there, now I'm at 14.2003 megahertz. So that confirms not only the Tayloe detector is working, but also the audio switching is working correctly for the for the Tayloe detector. So a lot we've proven there. What I'm going to move on to now is basically put that phase shift plus add logic in the code. I'll call that test receive phase shift, and what we should see there is depending on the sideband we picked, one will be suppressed and the other will be present. So that's coming right up. Okay, so same setup as before, except now I've got the program test phase receive loaded into the ESP32, and what that basically does is it takes the left and right channel on the input side, it performs a 90 degrees phase shift with respect to those two channels, and then it adds them together and then sends the output to the audio output here. So I'm using the same input frequency as before, so this is 14.2001 megahertz, and the LO is set to 14.2 megahertz. So basically the output should be around about a kilohertz, and you can see it is indeed there. And that is the upper sideband. So if I go to the lower sideband, I've actually sort of included a little switch in there so I can change between the sidebands. You can see there's that sideband suppression at work. So now I'm receiving on the lower sideband. So let's just go down. I will go 1 kilohertz less than 14. And there you can see there's the lower sideband there. And let me just go to upper sideband so you can see that suppression again. And there's the suppression there. So one other way to measure the difference between the wanted sideband and the unwanted sidebands is put the scope in FFT mode and then measure the difference between the dBm of the wanted sideband, which is right here at 6.53 dBm, and then go down to the unwanted sideband, and that goes down to minus 30 dBm-ish. So the difference between the two, minus 30 to, let's have a look at that again, 6. So that's gives around about minus 36 dBs of suppression, which isn't bad, but I'm pretty sure I got better before. So I'm not quite sure. I have been noticing that this circuit here isn't performing as well as the previous example I did, and I've got that here just for reference. So this is the previous circuit, and obviously one of the big differences is I've got this ESP32A1S mounted on headers instead of soldered directly to the board. That perhaps could be something to do with it. Minus 36 dBs of suppression isn't too bad. What I'll do next, though, is I'm going to basically hook up an LCD and get the code running so that I can actually change the frequency and should be able to receive some signals, get this on the air, at least the receiver side, and then I'll probably wrap this video. So that's coming right up, and you know, as with the rest of these examples, I'm going to create a new Arduino sketch to have the simple receiver. In fact, that's what I'll call it, simple receiver. So anyway, that's coming right up. Well, I thought I was ready to get this this radio on the air, but I did a bit more sort of digging around in the performance of it, and as I mentioned before, comparing it to this earlier radio, the unwanted sideband suppression is much worse, and I'll give a demo of that later on. But so this is at 2 kilohertz above the signal coming in here, and you can see we're getting around about 3 dBm. As I change sidebands, that goes down to minus 34 dBm. So the difference is around about 37 dBs of suppression, which isn't bad, although comparing it to the other radio, it's actually much worse than the other radio. But one of the other things that I noticed is as I go up in frequency, you'll see, so we're up at 6 kilohertz above the let me just change sideband. So we're at 6 kilohertz above the input RF here, and getting good suppression here. But look, as I go up to tune up to 8 kilohertz above, we're starting to see some nasty products in the output here. And then if I go even higher, you can see even more nasty products in the output there. Let me just turn the FFT off so you can see that. So what this is basically, so this is on upper sideband, so it should be suppressing everything, and I'm 8.5 kilohertz above the input signal. And look at this messy output here. And then as I go higher, and then after around about 10.5 kilohertz, everything goes back to normal. What I initially thought is maybe there's something wrong with the Hilbert filter that I'm using, but so what I did is I put exactly the same code on this board, and there's none of those artifacts at all. So let me just give you a quick comparison to the other board so you can see that for yourselves. So here's the earlier radio I did, and I'll include a link to that series. So you can see I'm on upper sideband, and I'm 2 kilohertz above the input RF signal. So same signal, same software. You can see that here, so the unwanted sideband suppression, if you compare it, so we're minus 39 dBs compared to, looking right up here, 5 dBs. So the unwanted sideband suppression is about 7 dBs better on this radio. But the other interesting thing is as I go up in frequency, you don't see any of that nastiness that we saw in the output of the other radio. So I'm now at 9 kilohertz above the input RF signal. Absolutely nothing at all. So basically, given the software is identical between these two, given that these are both using ESP32A1S, so everything's identical from a software perspective, but there's some difference electrically between these two radios that's causing the problem in the newer radio. So it's going to be a mystery, a bit of a mystery to figure out what exactly is the difference. So there's obviously a lot more circuitry on this radio. We've got the input relays, we've got the kind of separate bandpass filter on headers here. We've got the ESP32A1S that's also on header. It's not soldered directly to the board. We've got this audio wire sort of with some flying leads here that could be the problem, but the upshot is I'm going to have to do some troubleshooting on this board to sort of figure out what exactly is causing the misbehavior here. Like I said, I don't think it's in the software. I mean, it certainly could be potentially differences in batches of ESP32A1Ss, perhaps. It could be, I noticed that here's the FST3253, and I'm not using exactly the same variety. I'm pretty sure they're both genuine ones, though. This one isn't a knockoff. I checked the op amp on the output of the Tayloe detector, and they're identical. So got me scratching my head here. What I'm going to do is I'm going to wrap the video right here and perhaps give you all a chance to think about what could be causing the difference between these two radios. So anyway, I'll include a link to the original radio, so if you're interested, you can have a look at the schematic and, you know, compare and contrast here. It's got to be something like, I mean, the output signals look like some kind of audio harmonics. So, but not quite sure what it is. But anyway, I'm going to wrap it here. I'd appreciate any thoughts and suggestions about what I could possibly probe and fix. And what I might do is do a follow-up. Well, what I will do is do a follow-up video to go through some of that troubleshooting. Anyway, I hope you enjoyed this video, even though we didn't get the radio on the air. I always enjoy the troubleshooting part of this hobby, so more to come. Catch you all later.